Hello.
Hello, how you doing?
Good. How do you install the lockdown browser on your computer?
You have to click on the actual device, on the actual quiz, and it gives you a link to that. So, if you're using a work computer, they might not let you at all. That's sort of the fun part. And sometimes Chromebooks have problems. But yeah, when you first click on that, the respond to test, it'll ask you to download something, and then you download it, and you might even have to update it at some point. But that's how it downloads basically a new browser. Have you tried to take the practice test yet? The respond to practice test?
Not yet.
Yeah, that's how it does it. That's why I wanted you guys to do it early, because you usually don't know until you do that whether your computer is going to be able to work with it. It's pretty well tested. I had like one student that had a Chromebook that it wouldn't work with, but I've had 50 students with Chromebooks that it did work with. So anybody else have any questions? Not very many people here. I'm actually going to give you guys an option. Of course, it's a bummer that I'm making the request, but I only got 6 of you guys in here. But if you want to, I can allow y'all to wait until Monday to take the test. We can do the midterm Monday as opposed to Wednesday. I've already moved it for one of my classes. Like I said, I'm willing to do it for you guys too if y'all are interested.
For me personally, that'd be better because on Wednesdays I have lab right after this class, so I wouldn't have to use my brain in this class and then just go using my brain again.
Yeah, that's a good side of
whatever.
the Monday and Tuesday classes is you don't have to. You don't have to. Usually, you don't have a lab right after if you're in my class, at least. Because my Monday class is just morning and then this evening class with nothing between, but doing work. Looks like Jared agrees with it. Jacqueline agrees with it. Rebecca, yeah. So I say that's close enough to a majority for given the number of people that are here. So we'll go ahead and move it back to a week from today. And that gives me more time to make sure you guys get plenty of practice on the practice test. I had some issues with the practice test, so it took a little while. I'm going to change the date on the, well, no, I probably shouldn't. I'm still going to keep the date on the respondents practice test because that date is what's compelling you to take that early. So if you don't take it soon, it's going to disappear and then you'll be up the creek. So make sure you guys go ahead and take the practice respondents test first. The reason behind that is one, to make sure your browser works, but two, actually allow you to see the correct answers when you do that test. But you're only allowed to take it once. So I'm trying to sweeten the deal by getting you guys to do it by me letting you see the corrected answers. So hopefully you'll do that. Does anybody have any other questions? You are allowed an equation sheet. I've pointed out throughout the semester any equations that I said you could use even if they're not labeled in the book, but generally other than that, it's just the equations in the book that have numerical values by them. Like if you look, there's an equation 7-8, which means the 8th equation of chapter 7. So it has a parenthesis, a 7 dash, and then an 8, and then another parenthesis. All of the equations with numbers next to them like that are fair game. You can put them on your equation sheet, and you're going to have to hold up your equation sheet in front of the camera and put it close enough where I can make out and read every detail, and then turn it over and do it again. So I can see both sides, and you're going to do that with every sheet of scratch paper you have. So if you want to bring scratch paper, that's certainly acceptable, but you don't want to bring too much or you'll have to waste a lot of time. I'm going to allow you guys to start up to an hour early. And the deal is you get 2 whole hours, and this class is an hour and 15 minutes. So I'll let you start, say 45 minutes early. And if you run out of time, that'd be because you started late. In other words, if you started at 5:45, which is the time class starts, I'll give you another 45 minutes at the end where you can finish it. But if you start later than 5:45, you're not going to get your full 2 hours to take it. So make sure you start it no later than 5:45.
How many questions is it?
I think I have 4 or 5 concept questions, and I want to say 6 or 7 problems.
Okay, thank you.
No problem.
And we're doing it during class time?
Yeah, you actually do it during class. Just the midterm and the finals, so I do actually during class times. All the other tests are online and do it when you want.
And we can come earlier and have
Yeah, I'll
that
open
time
up.
and full class time?
Yeah, I'll open up at least 45 minutes early. And then I'll leave it open at least 45 minutes late, so you can fit your 2 hours, whichever way works. If that time can't work, like if you have a class immediately before and immediately after, and you have to attend those, let me know, and I'll just have to make you a different test and let you take it at a different time. There is no real good way to find all the equations other than just flipping through the pages. So yeah, just flip through chapters 1 through 7, and then use that sheet for your final too. Just add to it when you go to do the final, because the same thing's going to happen. Don't just toss it. You're not allowed to write any sentences, but you are allowed any of the inside cover information. I know that many of you don't have an actual physical copy of the textbook. You might have a binder ready version, or you might just have an ebook. But in the binder ready and the hardcover and paperback versions, there's inside covers that have conversion factors, SI prefixes, constants like G, gravitational acceleration, or speed of light, stuff like that. You're allowed to have those, as well as tables for derivatives or integrals if you wanted. But I would not write those out. I guess you could if you don't have that many. We haven't used very much. But you're allowed to just take a copy of the inside cover of that book, or you can go to the library and make a copy of one of those inside covers of a physics textbook. And you'll have to have a photo ID, so don't forget that. So we did decide we're going to go ahead and have the test on Monday as opposed to next time. I guess I'll go ahead and get started. I have a couple examples I want to work for you regarding chapter 8, and then I'm going to go ahead and jump into chapter 9. After chapter 9, we're going into relativity, and then if I remember correctly, we jump back from relativity, which is like chapter 36 or something like that. Then we'll jump back to chapter 10, and I think that's about it. Oh, we jump to 14 and 15 after that for oscillatory motion and springs and stuff like that. So anybody have any questions before we get started? All right, so the first thing I want to do is, actually I just dropped the pen. I get it. Oh boy, that's really far down there. Woo. Sitting on a bar stool is not fun. Trying to bend over and pick that up. The first question I want to do is I'm going to attack a problem you maybe hadn't thought of, but it's a projectile motion problem. So let's imagine a projectile is going to be fired off of a cliff, and specifically, let's say it's a golf ball. So we'll say we have a golf ball, and it's off some high cliff whose height is 100.0 meters. That's going to be H, and it's that many meters over a flat valley, if you will. Okay. Let's say we hit a golf ball such that it leaves at an angle of 37 degrees, which is about 36.9 degrees. So I'll call it 36.9 just to be pedantic. 36.9 degrees. That's an indicator, a very specific indicator of something special there. And we're going to fire it at 25.0 meters per second at 36.9 degrees above horizontal. It's going to take off, reach its max height, and then come over here and land. What I want to know is H max and V final. Okay. Now, by saying V final, I'm going to go ahead and put this up here. So I want you to actually be able to find the actual vector, not just the magnitude. And that's sort of the neat part about this problem, is it allows me to get you to solve a problem that's not normally the case with conservation of energy. So we're wanting to use conservation of energy to solve this. Now, you already know something about how to solve such a problem. For instance, in projectile motion, we use kinematic equations. So I could solve for this H max right now using kinematic equations. For instance, I know that this velocity has a vertical component and a horizontal component. And since we're ignoring air resistance, the horizontal component is going to stay the same. and the vertical component is going to decrease, 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 come to a stop. In other words, reach zero, and then fall, 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 right? So if I look at my triangle, what I have is 25.0 as a hypotenuse, 36.9 degrees here. So that means this side would be 30.0. Excuse me, that's 15.0. Sorry about that. And this side would, of course, be 20.0. So in other words, this is a 3, 4, 5 triangle. The 3 is here, opposite 36.9. The 4 is here, and the 5 is there. Obviously, this is 5 times 5. So I have to multiply the 3 by 5 to get 15. I have to multiply the 4 by 5 to get 20. So that's my components of velocity, if you will. So now that I have that, I can just use a kinematic equation. For instance, I can use v squared is equal to v0 squared plus 2ax minus x0. In this case, we're actually treating the vertical motion, so I would be advised to call that y and y0. So what I know is the vertical velocity here is 0, because at that point, the velocity should be perfectly horizontal. V max, or v at h max, should really be about 20.0 meters per second. Okay, so with that in mind, I can say the final velocity vertically is 0. The initial velocity vertically is 15.0 meters per second in the upwards direction squared. The acceleration is going to be negative, so it'll be plus 2 times negative 9.80 meters per second every second. And then times the h max minus the initial height, which I'll say is 100 meters. Okay, so it's like I'm treating my origin as if it's right here. So that's easy enough. We know what 15 squared is. I'm pretty sure that's 225. So I get 225 meters squared per second squared is equal to 2 times 9.8 would be 19. 2 times 9.8 it'd be 19.6. I don't know why I doubted that, but I did. So this would be negative 19.60 meters per second every second times h max minus 100.0 meters. So what I want to do now is solve for this h max. So I'm going to divide 225 meters squared per second squared by 19.6. Well, 19.6. I don't know why I wrote a 2 there. Meters per second every second. That's obviously going to leave just meters, and that's equal to h max minus 100.0 meters. So finally, I can say h max. I think I end up getting 111.48. So let's do that. 225 divided by parentheses 2 times 9.8. Just checking my work. And now I add 100 to that, and sure enough, I get 111.4796. And obviously, I've carried a bunch of extra sig figs there, but that's my H max, and that's just doing it with kinematics. So, and the only reason I did that is I want to show you that I get the same answer whether I do it with kinematics or whether I do it with conservation of energy. Now, the conservation of energy equation that I showed you was this U initial plus kinetic energy initial plus work in equals U final plus kinetic energy final plus work out plus E loss. Now, remember, I gave you all these terms, but in reality, what that means is you can add as many terms as you want. If you've got 3 or 4 different sources of energy being put into the system, then you need 3 or 4 terms like this. This would only be one of them, right? So you might have one for a father pushing a daughter on the sled. You might have another one for an engine or a blower, say, that's actually projecting wind out that way and conservation of momentum is giving it energy this way. So you have a second term there. And the same thing on the other side. If you're losing any energy or compressing any springs or something, you can add more terms over there. The main thing is you want to count everything that adds energy or takes energy away. The things that add go on this side, things that take it away go on this side, and only count them once. Count everything, but count it exactly once. So in this case, I'm going to ignore air resistance and everything, but I want to know the velocity at this point, and I want to know H max. So H max is what I'm going to do for part A, and part B is, so H max is what I'm doing for part A. For part B, I'm wanting to find that final velocity. So let's do part A. Well, for part A, the potential energy initially is, of course, M times G times little h, and the kinetic energy is 1/2 m v initial squared. The work in is 0 because we're only inspecting it the instant it leaves the golf club head, which we're assuming at 0 height on the cliff, and that's equal to U final. Now in this case, the U final is mgh max. But the final kinetic energy is not 0. As we saw, it's going to have a velocity of 20 meters per second to the right. So I'm going to say plus 1/2 m v h max squared, like that. Now, the first thing you notice is that the mass, which I wasn't given, is canceling out, and that's good because we couldn't have solved it otherwise. So what I can do is multiply through by 2, and I'm trying to solve for this H max. I know what that is already. So what I'm going to do is multiply through by 2. I get 2gh plus v0 squared is equal to 2gh max plus vh max squared. So vh max, I'm going to have to take a square root to get that, but I think you can see what it is. It's going to be v0 squared minus 2gh max minus h. And then I take the square root of all that. Notice that looks just like the equation we just used. V squared is equal to v0 squared plus 2ax minus x0. That's exactly the same equation. See, 2ax minus x0 or y minus y0. So yeah, it should absolutely give you the same result. The square root of 25.0 meters per second quantity squared minus 2 times 9.80 meters per second every second times, oops, dumb me, I was solving for velocity H max. I completely got lost in my own problem. Remember, I'm solving for this, not for that. I don't know why I did that. Maybe because I got excited about showing you that it comes out to be the exact same equation, but either way, Mr. Y has Alzheimer's. Not really, but my grandmother did, so it is a constant concern of mine. So scratch that for a second. Let's go ahead and solve for H max this time properly. So I'm going to say V0 squared minus VH max squared, that's that and that on the same side, plus 2GH is equal to 2G H max, which is what we're really solving for. So now I can divide everything by 2G and I'll get H max is equal to V0 squared minus VH max squared over 2G and then plus the initial height, which even looks exactly like the formula we did earlier. So I can plug all this in. 25.0 meters per second quantity squared minus 20.0 meters per second quantity squared over 2 times 9.8 meters per second every second plus 100.0 meters, which gives us again 111.4769, if I remember, 4796 meters. So we did exactly get the same result that we did before. In fact, even the formula was exactly the same. So we know that was right. Now, because of that, because I've made this nice little screw up, I don't have room to do part B. So I'm going to do part B now as follows. So let's say I do it like this. This way you can still see the original problem. Okay, so there's the original problem. I'm going to do part B now. So part B is I want to find that final velocity. Well, all I have to do is U initial plus kinetic energy initial plus 0 is equal to U final plus kinetic energy final plus 0 plus 0. Again, I'm ignoring work in, energy losses, air resistance, all that good stuff. So what I have is mgh plus 1/2 mv0 squared, which remember v0 is that quantity, the 25 meters per second. Okay, plus, since I called this the origin, so that this height is 100 meters, that means this height must be 0 meters. So the other side gives me 0, because that's m times g times 0, plus 1/2 mv final squared. Now this is going to be the magnitude, excuse me, this is going to be the magnitude of the final velocity. I actually asked for a vector quantity, so I got to work some of those details out when I'm done, but it's pretty straightforward from there. I think you can see that again, the masses cancel out. And dang, I just stuck a pin halfway across the room. Okay. So the masses cancel out. And this time I can solve for V final by multiplying through by G again. And what I'll get is V final is equal to multiplying through by 2. I get V0 squared plus G times H minus 0, basically, because that's that term right there. I'm just trying to show you again that it is exactly the same equation that we had from kinematics. So I can write this in, and I'm going to say that I get the square root of 25.0 squared, leaving the units off this time, plus 9.80. By the way, G is always positive in conservation of energy. And then times 100.0 meters. So that's meters per second times meters. So that's meter squared per second squared, just like this. So we can see it does give us exactly what we want. And I think it comes out to about 50.23, if I remember correctly. So let's say 25 squared plus 2 times, yeah, I left all this 2, don't forget that. Remember, I multiplied through by 2 with this, so that 2 has to be there. So pay attention to that, because clearly I didn't. So now I'm going to do this work. I'll say 2 times 9.8 times 100, and I get 2,585. And that's meters squared per second squared under the square root. So I take the square root of that, and I get 50.84. 843, say, meters per second. So now what that is, that's the final velocity completely. So when we looked at it in our original drawing, it was at some angle. So what I would like to do is sort of say, okay, well, let's say it has this horizontal component that we already know is 20.0 meters per second. Now what we just discovered is that it has an actual hypotenuse of 50.843 meters per second. And it's got some other obviously vertical components. So we might want to find that angle phi right there. Obviously, this is adjacent and hypotenuse. So what I'm going to do now is I'm going to say, okay, cosine phi is equal to adjacent over hypotenuse, that's 20.0 meters per second over 50.843 meters per second. Again, extra digits there. And this is going to give me phi is equal to cosine inverse of 20 divided by 50.843. And I get 66.836 degrees. Okay. So that's the angle, and that's the V final. Any questions on that? So I did this problem specifically because when you do conservation of energy, you almost never have to deal with vectors. You don't have to do any, breaking down the components. And if I had thrown the ball straight up with an initial velocity of say 15 meters per second, then I wouldn't have had to do any of that stuff. But because this problem was actually a two-dimensional problem, I did have to use some vector stuff to, for instance, to make sense of what the velocity was when it got to the top of its projectile motion. And that was hinging on the fact that the horizontal velocity is not going to change because we ignore air resistance. So any questions on that? Okay, so let's try another one now. So here's example 2. What I'm going to do is imagine the Earth being right here. And then I'm going to imagine a spaceship of mass little m, say, being right here in the apogee of its orbit. And what I'd like to find out is what is this V right here. I want to say V sub A because that's apogee. And I'm going to say that's 9,000 meters per second, which is a very normal speed for things in orbit. Okay. I'm going to say that, in fact, the center of the Earth and this distance are the same, even though I clearly drew it differently. And I'm going to say they're 825 kilometers, 825 kilometers. So this side right here, from here to here, is 16,000, excuse me. Actually, I want 8,250 kilometers. And I don't know why I wrote kilograms up there. So this is going to be 8,250 kilometers. And this distance also is going to be 8,250 kilometers. So that this is 16,500 kilometers. Okay. What I want to know is V. This is actually VA, and that, I mean VP, and the other one's VA. I drew it backwards. I'm sorry. So let's call this VP for perigee, and this is VA over here, and that's apogee. So apogee implies farthest, and perigee implies nearest. Okay, I want to use conservation of energy to do that. Well, we had found that potential energy for radii or for distances from the center of the Earth that are well under the distance, well under the radius of the Earth, we had found U is equal to mgh. But it turns out that's completely inadequate if we're talking about forces beyond, 1 Earth radii or even comparable to 1 Earth radii. In fact, the formula for any distance r is negative g m over r. okay, for any distance r, and m is the mass of whatever planet. In this case, the mass will be the mass of the Earth, so I'll put that little mark on it. Okay, now you might recall this formula came up when I calculated the work done in taking an object from the surface of the Earth out to infinity, and I got a positive value for this. Well, that was the work done in pulling it out here. The potential energy is actually the negative of it, because it turns out that work done by the system, which in this case you'd say the system is the actual satellite or whatever, is equal to the negative change in potential energy. That's just a rule that you're going to have to commit to memory and think about it a lot and use it on occasion until it makes sense to you. But using our old equation, U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. I'm going to just assume all these things are zero, because you're talking about a satellite moving through near a vacuum that is space. So I'm going to put all those zero, and we're just going to deal with U, I, K, I, U final, and K final. So I can put all this in. I will say at this point right here, this is perigee, and we'll call this distance, let's say RP for R perigee. And notice that happens to be the distance from the center of the Earth to there. It also, even though its drawing is not to scale, it's the distance from the center of the Earth to the center of the orbit too. That's why this is twice as big as that. So what I'm going to say is my potential energy initial is the gravitational constant of the universe times the mass of the satellite times the mass of the Earth divided by RP. And there's a negative on that. Plus 1/2 mVp squared. That's the initial kinetic energy, where Vp is that 9,000 meters per second. Now over here, I'm going to have a negative Gm Earth again. But this time, notice if this is RP, this is also RP, and then this is 2RP, so this would be 3RP. So I get that plus 1/2 mV. In this case, it's the apogee that we're wanting, so that's the square there. We can already see that the m's of the satellite cancel out, which is good because we weren't given that again. Okay, but I'm going to also multiply by 6, because I see there's a denominator of 3 and a denominator of 2. And the least common denominator, of course, would be 6. So if I multiply through by 6, I'll have no denominators except for the r's, which is not that big a deal. So I'm going to multiply through by 6. Don't have to do this. It's just a way to do it. So I'm going to get negative 6 G mass of the Earth over RP plus 6 divided by 2 is 3. So I'm going to have 3 VP squared is equal to negative 2 G mass of the Earth over RP plus 3 VA squared. And the VA is what we're wanting to know. So I can say VA squared, at least, is going to be equal to, if I pull this over here, this one's going to become positive. So I'll say G times the mass of the Earth over RP. And then when it's over here, it's positive. So that 2 is going to be positive, and this 6 is going to be negative. And then I'm going to say plus 3 VP squared. And then, of course, I have to divide everything by 3 because the VA was multiplied by 3. So in doing that, I now have VA is equal to the square root of GM. Notice this 2 minus 6 is negative 4. So that's going to be negative 4 over 3. And did I actually do that right? I'm going to take a square root. I know that. When I pulled this over here, this became, oh, when I pulled this over here, this became 2, and this one was -6. Yes. And this was plus, so that works fine. 3VA squared, 3VP squared, VP, RP, that makes good sense. I feel like I'm getting a negative in here, and it might be a negative, we'll have to see, but I'm going to get -4 thirds G times the mass of the earth over RP plus this 3 divided by that 3 would be VP squared. And that should be our whole answer. So let's punch it out in and see if it is actually a positive. It's definitely going to slow down. We can see that, and we expect that from Kepler's laws of planetary motion. They sweep out equal areas in equal time. Well, the sweeping is done by a smaller radius vector here and a huge one there. So the area out here has to be quite a bit narrower than the area in here. So it's going to slow down quite a bit out here. So when I do this computation, I'm going to take, so y'all can see it, I'll say negative parentheses 4 divided by 3 times 6.67 e to the negative 11 times 5.98 e to the 24. That's the mass of the earth. And then I'm going to divide that by the 8,250. So 8250 times 10 to the third, because it's kilometers. And that gives me a negative 64 million, basically. Now I'm going to add to that 9,000 squared, and that's going to give me the square root of 16.537 meters squared per second squared. When I take the square root of that, I get 4.067 times 10 to the third meters per second. So it went from 9,000 meters per second to about 4,070 meters per second. Any questions on that? I'm going to tell you to see page. Let me double check my page number on this, because I did a derivation of this negative GMM over R in the last class, but I just basically borrowed that result to state that the work is equal to the negative change in potential energy. And I wanted to just point out to you in your textbook where it's going to be. I think it's page 199 and 200. Yes. So I want to say see pages 199 through 200 of your textbook to find out about that work equals a negative change in potential energy, and how I got that as my potential energy for an object that's really far away from the center of the earth. Does anyone have any questions on that? Nada? Okay, well, that's really all the types of examples I really cared to make sure I do for you. I mean, you can see a lot of other examples in your textbook, and your homework's going to give you a lot of chances to do some more of those, obviously. But what I want to do now is go ahead and get into chapter 9. And chapter 9 is called linear momentum. So chapter 9. Is linear momentum. And linear momentum is actually given the symbol P. It's a vector quantity. And generally speaking, it's mass times velocity. However, if you want to talk about the momentum of a system, you can do that as well. And then it'd be the summation from I equals 1 to N of P sub I plus of just p sub I, which is also, of course, equal to the summation from I equals 1 to n of m sub I v sub I, just like that. Sorry, I keep wanting to put pluses because I'm not used to writing the summation symbol. So yeah, basically you take each object's mass and multiply it by the vector velocity, and you'll get a vector sum, and that vector sum has a magnitude and direction, and that will be something that's a property of the system, because it turns out when Newton actually wrote his second law of motion, he didn't really write F equals ma. Remember, I actually expanded that to say summation of the forces is equal to ma, and that's sort of the version we've been using this whole time. In reality, what he said was the net external force, so I'm using that sigma notation to represent that, is actually equal to dp over dt, where p is the mass times velocity. If you look at it that way, you can say, oh, d by dt of m times v, if m equals a constant, then you get m dv dt, which is ma. Okay, so in reality, this is a more general expression, because now I can take into account the fact that an object's total mass might be changing. So that was Newton's second law and the way he initially stated it. In many cases, of course, where the mass is a constant, we can say mass is a constant, and then we get back that ma or mdv dt, and that's fine. Now, look what happens, though. If you assume /no that the summation of forces is equal to 0, then you get this nice sneeze expression that dp over dt equals 0, which means p is equal to a constant. And that's what we call conservation of momentum. So just like we talked about conservation of energy, we weren't like telling people to, turn down their heaters or anything like that. We were saying, no, there's a fixed amount, and that amount will always be the same. That's what we mean by conservation in physics. It has nothing to do with like conserving energy. It has everything to do with, there's a fixed amount. You can put it in a Ziploc bag, and you can imagine the Ziploc bag having little baffles in it or whatever, like this. So there's your little Ziploc bag, and you might have a semi-permeable membrane between the two. And this side would be kinetic energy, and this side would be potential energy. And since it's a Ziploc bag, the total amount of air in it doesn't change, but I could squeeze this side, and this side will get fatter. And then I could squeeze this side, and this side will get fatter. And that's what we mean when we say conservation. So now we're saying conservation momentum, and that just means m times v is going to stay a constant. So we can, for instance, use that to analyze collisions, not unlike we did with skid marks, to figure out how fast the vehicle was going before it actually collided with something because of the length of its skid marks. But we can also now predict things like, which direction it will go and stuff like that. Now, the other neat thing about this is we can also introduce something called an impulse, and that's kind of handy as well. So for instance, we can say on average, F average is just change in momentum divided by change in time. Okay, you can take that in one dimension, in which case you don't have to do anything about the vectorness of it, because it's all in one dimension. Or you can actually take it in multiple dimensions and get something else out. The other thing you could do is you can say, well, F is equal to dp dt. So you can say, if you have F as a function of time, you can multiply that by dp dt, and then you say the integral of dp dt from t equals 0 to some t final, and then integrate this side again from f0 to f or excuse me, yeah, F0 to F, then what you end up getting is that the change in momentum, delta P, which is P final minus P initial, which you could also write as P of T final minus P of T0. This is all vector quantities, of course. You could do it in one dimension and reduce it, but that's going to be equal to the integral of F of T dt. Okay, and this whole thing is called impulse. But it's kind of helpful because you've probably been told stuff like this before if you've ever played baseball, softball, volleyball, anything like that, or tennis. You'll hear people tell you to hit through the ball. Okay, that's because of this. You can see the change in momentum, which is what you want to maximize if you want to hit a home run, for instance. You want, no matter what the initial momentum of the ball is, that's set up by the pitcher and air resistance. You want that maximum momentum out to be as large as possible so that you can hit the ball as hard as possible and therefore it leave as fast as possible, maybe even go over the fence. Or in the case of tennis, you want it to hit it hard enough that it's so fast that the player can't get to it, but you of course want to keep it in. So you put some topspin on it and that helps keep it in. And baseball and softball, though, it's really just trying to hit it as far as you can in many cases. So the way you do that is you've got to either make sure the force is a maximum or that the time that the force is in contact with the object is a maximum. So if a ball happens to be coming, let's talk slow pitch softball for a second. If a ball happens to be coming like this to you, okay, when they say hit through the ball, what they really mean is your bat should go straight along that same line. So that you're actually exactly anti-parallel to the ball. Okay, by doing that, you get to touch the ball way back here and continue to touch the ball all along here. So you're maximizing this dt, this F times delta T. So in the terms of the average, delta P is equal to F times delta T. So that's another representation of the impulse. The impulse, by the way, has units of Newton seconds, but that also happens to be kilograms meters per second because that's mass times velocity. So that's one of the things you do. If you see someone playing tennis, a lot of times when they first learn, you'll see their tennis racket looking sort of like this from the edge on anyways. And you'll see them just basically swinging it up and down and the ball goes plip like that, right? That's bad, okay? Because what's happened is the person knew they wanted to put topspin on it, so they put topspin on it, but they didn't really hit through the ball. So really what you got to do is you want to take and swing that tennis racket like that so that it goes. So you start touching the ball right here, and now you're actually rolling up the ball, and that gives it the top spin that it needs. So the ball will leave this way. And when you study fluid mechanics, it'll make perfect sense that the velocity on this side of the ball is slower than the velocity on this side of the ball. As you can tell, the friction of the ball up here is going to slow down some of the air coming over top of it. So that's going to be a slower velocity. This one's going to swiftly pull the air by it and make it go even faster. So high velocity means low pressure, and that sucks the ball downward. So that's the Bernoulli effect, and that's why we top spin with a tennis ball, a tennis racket, or even a ping pong paddle. So anyways, these are some of the major concepts regarding momentum, conservation of momentum. You might want to know, well, what is the type of problems we can solve with that? Well, let's consider one. So this is going to be example 3. So let's imagine that a tennis ball has a mass of 0.0590 kilograms. It's about 59 grams basically. And let's say that we want to hit the ball at, I don't know, let's say we'll hit it at 120 miles per hour. So let's say V equals 120 miles per hour, which we know 60 is 26.8. So this would be 53.6. Okay. And let's say, for instance, that we'd like it to let's say that we would like it to do this with a contact time, delta t, on the order of a microsecond. So let's say t is 0.003000 seconds. What force must be required? Okay, so we're looking for really an average force here. So what we know is F average is equal to delta P over delta T. Well, I want to start off at V0 equals 0 meters per second. So my delta P, which is P final minus P initial, as I told you, deltas always mean final minus initial. That's going to be 53.6 meters per second minus 0 meters per second. That's just the velocity time part. Now I multiply that by the mass part. So I can get that the change in momentum would be, if I can ever get my calculator to come on, 53.6 times 0.059 gives me 3.1624 kilograms meters per second. Okay. Well, that has to be equal to F average times delta P. So F average, the force that I need to apply with the strings of my racket, times 0.00300 seconds has got to equal 3.1624, which really should not have these extra last two digits, kilograms meters per second. So I can get that F average is equal to 3.16 divided by 0.003, and that gives me 1.0541 times 10 to the third newtons. So these two are extra sig figs. So we're talking about 1,000 newtons, and remember a 1,000 newtons, or remember a newton is about a quarter pound. So we're talking roughly 250 pounds of force is what a tennis racket would have to supply to hit 120 mile per hour serve. Any questions on that? It's actually a little bit more than 250 pounds, if I remember correctly, because of Newton. Actually, it might be a little bit less. Sorry about that. Okay, so any questions on that one? Any questions about anything? Okay, let's look at another typical problem. I'll call this, what time is it? Okay, I'll call this example 4. So this is a this is a skimboard problem. So you toss a skimboard, a 3.00 kilogram skimboard, is moving at, let's say, I don't know, 7.00 meters per second. So we know 26 is 60. So this is about what, 1/4 of that. So it's about 15 miles per hour. That's a little faster than we generally want to throw our skimboard, but we're going to go with it. It's moving at 7 meters per second. And we have, and by we, I mean probably me, have a mass of 120 kilograms. How fast will we go after I jump on? So this is a case where basically we've got a little skim board that has a momentum equal to P skim board is equal to 3.00 kilograms times 7.00 meters per second, which gives me 21.0 kilograms meters per second. And we have me really flying now, okay, having a mass of 120 kilograms, moving at let's say I'm moving at around 6 meters. Let's say, ooh, that's really unlikely for me. Let's say I'm moving at 5 meters per second. Okay. Okay, that's going to be 600 kilograms meters per second. So P total initially is equal to 621 kilograms meters per second. But now that's also equal to, instead of a 120 and a 3, now I've got 123 kilogram mass, P final. That's going to be 123 kilograms times V final. So setting these equal, I can say, well, V final is going to be 621 divided by 123. So I say 621 divided by 123. And I get 5.05 meters per second. So when I jump on the board, I'm way heavier than the board. So my momentum is going to decrease the momentum of the board quite a lot, right? So the board was moving at 7 meters per second. I was only moving at 5. Luckily, I came from in front of it a little bit so I could jump on it, and I jumped on it at moving at 5 meters per second. That slowed the thing down to 5.05 meters per second. And of course, I was expecting it to go 7, which is exactly why I fell over the front and hurt myself. Not an unrealistic scenario in my life. So does everybody see? That's what we call a perfectly inelastic collision, because basically what happened was the two things got stuck together. And that's a common problem. When two objects get stuck together, we call that a perfectly inelastic collision or an inelastic collision. And that's a special collision because if you're doing it in a center of mass frame, which is something we use in physics a lot, the two objects come together and come to a complete stop. So all their kinetic energy is completely destroyed. So there turns out to be, if your collision is elastic, then elastic collision means the conservation of kinetic energy is held. In other words, if you added my kinetic energy and the board's kinetic energy before the collision, and then after the collision, you added them, you get exactly the same values of kinetic energy. That would be an elastic collision. This, on the other hand, was a perfectly inelastic. Okay, and anything short of perfectly inelastic is a form of inelastic collision because some kinetic energy is wasted. Any questions on that? All right, well, we've got a little bit of time left. So let's look at another type of problem. Let's consider, for instance, two objects colliding. Let's say in this case, we're going to have, supposed to be example 5. Okay. So let's say we have a train. Obviously, that's a funny train car, but anyways, we're going to say the mass of this train car is 2,000 kilograms. And I'm assuming that's 4 sig figs. And let's say it's moving at 12.0 meters per second. When it slams into another train car that happens to be slightly overloaded, we'll say it's 2,500 kilograms, and it sticks together. So ultimately what happens is you now have them moving off with a final velocity equal to question mark. This one was sitting still. We'll just assume these are nice empty, or train cars only loaded with inanimate objects, say shipping supplies or something. Okay, so what we'd like to know is what's the final velocity. Well, the momentum total before the collision is actually going to be 2,000 kilograms times 12.0 meters per second plus 2,500 kilograms times 0 meters per second. Now, this is all in one dimension because they're train tracks, right? And on the train track, everything's going basically either north on the train track or south on the train track, or east on the train track or west on the train track. So this whole thing turns out to be basically 12 times 2 gives me 24. So this should be 24,000 kilograms meters per second. Now, the total momentum after the collision, P total final, is going to be 4,500 kilograms. Notice I just added 2,000 and 2,500 times V final. So if I set those two equal to each other, this is just like the skimboard problem. I got 2,400 kilograms meters per second is equal to 4,500 kilograms times V final. And you might guess, since this is slightly heavier than the other one, the velocity should be less than 6, right? Because we just added on another mass that had 0. And if it was exactly the same, you'd expect it to drop down to 6. So this is another, what, 25% bigger. So maybe it should be 25% less than 6. Well, let's calculate it. So we get V final is actually equal to 24,000 kilograms meters per second divided by 4,500 kilograms. And I get 5.33. Meters per second, which really you can think of this as 5 1/3 meters per second. And of course, a third, well, that goes into it 2 times. So yeah, that's on the order of roughly a quarter. So that's not too far off, but we definitely got what we expected, which was clearly less than half. Any questions on that? So there's a lot of neat little problems like this you can do. I'm going to make sure the chapter 9 date is corrected. If it's not already, I'm going to make sure it's corrected by sometime tomorrow. So now you want to start talking about doing your chapter 9 homework as well, even though it shouldn't be due until, I might get it done this week, in which case I'd make it due on Sunday, but you already have, chapter 8's due on Sunday as well. So I might, well, this would be Wednesday anyways, but the homework, the conceptual homework might be due this coming Sunday. So at least start doing the conceptual homework for chapter 9. I'm going to go ahead and let you guys go. Does anybody have any questions? Is anybody even there anymore? It's so exciting. All right, well, next time I'll talk about elastic collisions, and I'll derive some very useful formulas and show you how you can analyze things in 2 dimensions. Like one of the labs I used to teach my class, and I'd like to get back to doing that at TCC as well, is we'd have a air puck like on a air hockey table, and it would have a little electric wire running to it that would send sparks out every 60th of a second. And we lay it on a piece of newsprint with a piece of carbon paper under it. And each time, each 60th of a second, a dot would represent where this object is. And we'd have another one over here, and this would be like M2, and this would be like M1. And we'd give it a push with a velocity V1 and a velocity V2. And we could actually measure it because we knew each of the dots was 1/60th of a second apart. And we'd see them come together like this and then go off like that. And we could calculate the velocity before the collision because, you know, we could obviously just set up the coordinate system such that this is the x-axis and this is the y-axis. So we could get an angle and all that good stuff. We know the final velocities, V1 final and V2 final. Again, these are all vector quantities because we could measure them with protractors and all that good stuff. And from that, you could see whether conservation of momentum really occurred. And that's a really great problem. But in principle, you can actually solve this and find out, you know, what should this angle be and what should this angle be? Theta 1 final, and so on and so forth. So that's ultimately the sort of holy grail, if you will, of conservation of momentum is being able to solve those types of problems. As you can tell, this would require a lot. You've got a conservation of momentum in the x direction, conservation of momentum in the y direction. And if it's an elastic collision, then you could have conservation of kinetic energy. So you could have like 3 equations and you know, maybe 3 or 4 or 2 or 3 unknowns. So I will let you guys go. Remember, our test has been moved to a week from today. So make sure you take the Respondus practice test immediately, like today or tomorrow. Okay. It's going to disappear real soon. It has a deadline. If you don't get that tested, then you're not going to be able to download the Respondus browser. And that means you're probably going to have to come to campus and take the test on campus in a proctored setting. So everybody's free to go. I'll wait for the last person to leave so I can answer any questions.
Thank you.
Thank you. Mario, do you have a question?